Welcome everybody, and thanks everyone for joining us for our quantitative seminar. I am Abby Bratt. I'm from the Commerce Lab. I'm one of the organizers of this year's quantitative seminar, and I'll begin with a land acknowledgement. So the University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all bands and tribes in the Suquamish, Tulalip, and Muckleshoot nations. And our lab also acknowledges that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. So today's presenter is our very own Brielle, one of the co-organizers of the quantitative seminar this year. And Brielle Thompson is a third-year graduate student in the Quantitative Ecology and Resource Management program at UW, where she is advised by Julian Olden and Sarah Converse. And her research interests involve using quantitative models and decision analysis tools to help understand invasive species dynamics and inform decision-making. She is a proud Western New Yorker, go Bills. And she got her undergraduate degree at Houghton College, where she studied mathematics, biology, and education. Prior to coming to UW, she completed research at the University of Tennessee at the National Institute for Mathematical and Biological Synthesis, where she built models to guide free-roaming cat management, and she conducted research at Oak Ridge National Laboratory, where she built geospatial maps to inform potential corridors for black bears. Aside from research and to help her stay sane from coding woes, she enjoys running marathons. She just ran Boston, go Brielle. And with that, I'll let you take it away.
Cool. All right. So thanks everyone for coming out here today. I'm going to share my second chapter, which centers around a decision analysis concept called adaptive management. But first, I would like to thank the following organizations for funding and support. First, my two labs, the Converse and Olden labs, thanks to my advisors and everyone else in the labs. And for the Washington Cooperative Fish and Wildlife Research Unit, the Quorum Program, the USGS Invasive Species Program, and the USGS Science Support Program. So today I'm going to cover three main points. First, I'll explain adaptive management. Second, I will describe the methods to test adaptive management in a simulation framework. And third, I will apply this framework to a case study of invasive rusty crayfish management. Goes. All right. So a major theme of my research project centers around making better environmental decisions. And everybody makes decisions every day. This morning, I decided whether or not to hit snooze or wake up right away. I decided how many miles I was going to run with my friends, whether or not I was going to take the train and what train. And recently, I've had to make even harder decisions, like what graduate program I wanted to go to, and whether or not I want to sell my car. And I have to decide where I'm going to end up after graduate school. So it'd be nice if these harder decisions could be resolved by that magic 8-ball we all used to have when we were younger. We used to shake it up and help us make decisions. But fortunately, there exists more efficient ways to help people. So harder decisions often use decision analysis. And this is a quote by Ralph Keeney, who is a decision analysis researcher. And I really like this quote. So decision analysis is a formalization of common sense for decision problems that are too complex for informal use. So why do natural resource managers need a formalized approach to make decisions? Well, decisions they make are really urgent. They involve multiple stakeholders, multiple different groups, and these stakeholders have different objectives and what they're trying to achieve. So some want to minimize cost of management, or they want to save some species, so minimize effects to some fish, or they want to maximize recreational opportunities. And also, these systems are really complex. Trying to estimate what's going on in the environment is really hard, which I'm sure many of you understand. And also, it involves risk. So risk is the chance of an unfavorable event. So natural resource managers are pretty familiar with lots of risk. So a decision analysis tool that is used is called structured decision making, which is an organized approach to analyze complex decisions. So first, it involves defining your decision problem or the context of the decision. And then objectives are made, such as maximizing endangered species breeding pairs or minimizing cost of management. And these objectives consider stakeholder values and their preferences and tolerances. And then we think of different alternative actions, which will hopefully help us achieve our objectives. And then we predict consequences by using models and data while considering uncertainty in our system. Then we conduct some sort of optimization to compare alternatives. And then we decide the best alternative and act on it. So in this framework, structured decision-making starts out with defining a problem, ends with kind of taking an action. So it's a very linear approach. But this can be taken a step further, and we can learn from our actions through time. So this brings us to adaptive management, which is a special case of structured decision-making for current decisions made under uncertainty. So this was the figure I just showed in the last slide, but now we have adaptive management. So after we decide and take action, we can collect monitoring data, and then we can update our predictive models and then predict consequences, do the optimization, decide, monitor, and repeat that cycle. So in general, adaptive management can improve decision-making, especially for decisions where management is iterative and where resolving uncertainty is important. Because that through the process of monitoring and updating knowledge, the biological, environmental, and management uncertainty can be reduced. But there are some downsides to adaptive management because it requires stakeholder readiness, a decision-making framework, and campaigns to collect and monitor data. So it kind of involves this balance between resolving uncertainty and the time and money it takes. So in general, adaptive management is used pretty infrequently. So this is kind of old data from 2011, but it shows that 30% of the scientific articles on adaptive management had real-world applications. And in a large sense, 70% were non-implementation papers. So those are ones that just focused on the theory, the framework, and suggesting adaptive management. So a small chunk are actually like actual applications. But despite this, there are some adaptive management examples that I will note. First is one that I came across on my research, which is a really cool historical example. It's from the Yap people in Micronesia. So it's noted that the Yap people sustained a high population despite resource scarcity. So they learned how to create termite-resistant wood and maintain mangroves and seagrass meadows to support fishing. And they altered their environment by a process similar to adaptive management, and they undertook actions, observed and recorded their results through storytelling and songs, and they codified these practices through rituals. So that's a cool historic example, but here's a more recent one. This is the North American waterfowl harvest management. So this process started in 1995. It's involved using waterfowl monitoring data and projection models to decide waterfowl harvest levels for hunters through time. And a final example brings us to the East Coast on Delaware Bay, where an adaptive management study was developed to test different parameterizations for the link between red-knot shorebirds and horseshoe crabs. So the red-knot shorebirds make an annual trip to Delaware Bay, and they feed on these horseshoe crab eggs. But these horseshoe crab eggs are harvested, or in general, the horseshoe crabs are harvested for American eel and conch bait, and they're also used for medical purposes. So this adaptive management strategy kind of had to deal with those two objectives. So adaptive management has been used to guide management in various contexts, and it can be used in my area of research, invasive species management. So as I mentioned before, adaptive management is useful in systems where resolving uncertainty is important, and invasive species management is plagued with uncertainty. For example, biological uncertainty. Like, what is the abundance, the growth, survival, movement, etc. of these species? There's management uncertainties, like how should we manage, and will our management even work? Then there's environmental uncertainty, like how will climate change impact invasive species dynamics? And adaptive management could be useful in open systems like rivers, where uncertainty is high, since these invasive species have a variety of pathways that they can move and be introduced to into the system. So for example, take the invasive carp distribution in the Mississippi River Basin. Adaptive management would be really useful in here because there's a lot of real estate for these carp to move into, and adaptive management could help kind of inform the spread and different management strategies through time, and it could be a really extremely useful tool, but it hasn't been used yet. So this brings it to my application, which involves building an adaptive management framework for rusty crayfish in a riverine environment. So the main objectives of my project first involve building an adaptive management framework to simultaneously learn and manage. And second, I will integrate various monitoring data streams to potentially inform management effectiveness. So in the adaptive management framework, monitoring data is really essential because it's used to inform how management is performed. So a question I hope to answer is whether we need these additional data streams, and will adding these streams help us learn more about the system and help us make better decisions. So that's one big objective of my research. But for now, I'm just creating a framework that integrates only removal data. But eventually, this will be used to integrate various data streams like detection, non-detection, and radiotelemetry to kind of see how these different data streams compare in informing management. So let's look back at that structured decision-making adaptive management framework. First, I'm going to describe what I call the setup phase, which is defining the problem, the objectives, and the alternative actions. So I am applying this adaptive management framework for rusty crayfish control in the John Day River Basin of Oregon. And rusty crayfish are native to the Ohio River Basin, but they've been invasive in a lot of states in the United States, and they were introduced into the John Day River because most likely by a school teacher that released their school class project into the wild. And I guess they didn't want to build their class project, so they just put it into the wild. And so unfortunately, rusty crayfish presence is a big concern because they can spread rapidly, reach high local abundances, and they cause damage to aquatic plant beds that provide habitat, shelter, and nesting to a variety of socio-ecological important species like spring chinook, salmon, and steelhead. So the fundamental objective of this whole project is to minimize the ecological effects of rusty crayfish. So we'll achieve this by different means objectives, which include containing by minimizing the spatial extent of rusty crayfish, controlling by minimizing their population abundance, and then preventing by minimizing their movement of rusty crayfish downstream towards the Columbia River. So if a lot of you are from around here, and the Columbia River is super important. So you want to try to prevent rusty crayfish from entering that system to cause more issues to the Columbia River. So currently there's no management plan for rusty crayfish in the John Day River, but my project aims to simulate potential management alternatives with the goal to potentially inform decisions. So as I just described, we have different means objectives, which are containing, preventing, and controlling. And our management alternatives are linked to these objectives. So one alternative is to place traps at the edge river segments, which will help us contain and prevent their movement downstream. So this means that I'll place these traps in the river at the most downstream and the most upstream segments. That's what I mean by edge. And then another alternative is to place traps at the most abundant river segments. That's where population is the largest. And then a third alternative is to place traps where population growth is the highest. So although there is no current management plan within the John Day River, these alternatives are ones that invasive species managers are typically interested in. So that's why we chose these ones. So kind of going into more of the details of the management, it occurs June through September at 4 out of 10 segments. So what I'm going to show you today is just a small scenario. And the traps will be left out for 10 trap nights and 10 traps total per segment. And today I'll just be focusing on the final two management alternatives in my results. And in the future, I will integrate additional data streams to explore other monitoring alternatives to compare how well they do in informing favorable decision outcomes. But I'm going to take a little quick aside because it's important to note that my research involves an active adaptive management. So learning really motivates and guides the management, and the objectives incorporate uncertainty and the potential for learning. This is in contrast to passive adaptive management, which many of the marine folks in this room probably are familiar with because it's similar to management strategy evaluation. Let's see, chuckling over there. Because in that realm, learning is useful, but it's unintended, and your objectives account for the effect of management actions on resources. So in my project, I'm focusing on active adaptive management, and this learning is the key. So next I'll be moving on into this iterative phase, which is this adaptive kind of management part, which involves monitoring, updating models, predicting, optimization, and taking action. So my research is a simulation study. So instead of using data from real management, my monitoring data, I have to generate true system dynamics and monitoring, or what I have just removal data from a generated model. And then I predict system dynamics with an estimation model. So I have these two parallel models that are happening in this iterative phase. So I'm going to describe how these two models interact with each other in this adaptive management framework. And just as emphasizing this, the generating model simulates real world dynamics, and the estimation model produces estimation of the system, which is fitted using simulated data. So first we have our generating model for the first year. And then from the output of that, we get simulated removal data, which that feeds into that estimation model where we estimate the system. And in the estimation model framework, we have priors for our parameters. And for the first year, we have vague priors because we know nothing about the system yet. So it's pretty general. And then from that estimation model, we get our management decision. So say we have a scenario where we want to remove where population is the most abundant. Then we look at that estimation model output and see where in that whole river, where's the population most abundant? Then we look at that, and that's where we decide, and that's where we manage, which that feeds into that generating model, that true dynamics, because what we decide actually affects the real world. And then we get simulated removal data, and then we get an estimation model, which is, this is cool this time because now we can use posteriors from our first year, and they become our priors for the next year, which is pretty fun. And then we kind of continue that process. So we get, from the estimation model, we get a management decision, and then that feeds into the generating model, and then we have simulated removal data, and we continue that process. So this process of the posteriors becoming priors, that's Bayesian updating or learning. And this kind of approach is what I call, or what people call, forward simulation, which I'll describe a little bit. So the approach that I just described with the generating model and the estimation model kind of moving forward through time, that's the forward simulation approach. but often adaptive management problems are solved with stochastic dynamic programming, which is a little more complex, but that involves finite kind of solving for optimal management scenarios at a finite time horizon. These problems are solved with backwards iteration, or they're solved backwards in time often, which leads to a time and state-specific optimal solution. And these algorithms are super tricky, and often they require you to simplify your system. So it can't really model these complex systems because of the curse of dimensionality. And the stochastic dynamic programming informs optimal management scenarios. But with the forward simulation approach, we can model these complex systems because we're not constrained by solving for optimal management. So it's kind of easier to model these complex systems without being constrained by that. And in these scenarios, we get rules of thumb management rather than optimal solutions. And sometimes that's what managers actually want. And so that's why we're choosing this approach. So going back to our framework for the forward simulation, we have these two models. We have the generating model that simulates real-world dynamics, and management is informed by the estimation model. And this model I assume to be age-structured because it's kind of representing truth. And then we have an estimation model that produces an estimation of the system that's fitted using that simulated removal data from the generating model. And this model is not age-structured. So keeping these two models in mind, we can dive into the equations. For both the generating and the estimation model, they represent the same 3 steps. So first, crayfish are removed, then the remaining crayfish survive and reproduce, then the surviving crayfish either move or stay. So before I go into those different steps, an underlying assumption of my models is that they're divided into primary and secondary sampling periods. And this process is often referred to as a robust design, where data collection or removals occurs on secondary sampling occasions that are clustered within primary sampling periods. And population change and movement only occurs between these primary periods. So this general structure was defined by a model in 2018 that used removal data of failed chameleons to estimate and understand demographics. All right, so let's go on to the models of the different parts. And first, I'm going to describe the removal of crayfish first. But I will be describing all of the equations for the estimation model. And just as a reminder from earlier, this model is not age-structured, and it produces an estimation of the system. Oh, cheering for me. And so let's look at the estimation model. So first, we calculate population abundance at each of those segments and primary and secondary periods. So segments are modeled by the indices I. J represents the primary periods, K represents the secondary periods. So overall population abundance is a function of the prior abundance and the prior removals. But next, we calculate those that are actually available to be trapped. So you have a trap, and then there's some area around that trap where crayfish are attracted to, and that's the population that can actually be available for removal, maybe be trapped. And that's a function of the number of traps, the trappable area, and that population abundance. Then we calculate those that are actually trapped and removed. Those are calculated as a binomial random variable of the number that are trappable and the removal rate P, which we assume to be beta distributed. And this is a value between 0 and 1. And in the estimation framework, it starts out with a vague prior, but then through time, I'm updating that parameter value as I'm learning through time. Then at the end of this removal step, we calculate those that are remaining, which is the function of the final population abundance and that final removal. So that just described the removal process. But next, let's move on to the population change, where the remaining crayfish survive and reproduce. So I will describe this again for the estimation model. So after removals, we were left with that population that was remaining. Next, we calculate those that are available for dispersal after population change. And so this is a Poisson random variable with a growth rate G and that population remaining. But we have some interesting dynamics going on where for the months that are not June, we assume that this parameter value is beta distributed, which is a value between 0 and 1. And so during those months, only survival happens. But in June, that is when reproduction occurs. And we can model that growth rate as a gamma distribution, which is a value that's greater than 0. And we model that for June, and we can see here, this is not a rusty crayfish, this is a different one, but only Julie would know that. And you can kind of rip off those little eggs, so it's kind of just a fun fact. Anyway, that's my process of modeling population change. So finally, we can move on to movement, where the surviving crayfish move or they stay. But first, we have a pre-movement step. So we just calculated the number of individuals available for dispersal after population change, but some of them stay due to some cold temperature. So there's this probability that individuals stay because it's too cold for them to move. So some of those crayfish will stay. But then 1 minus that probability, we calculate those that are actually available to move, but still some of those crayfish will decide to stay. So that's how we get these two pre-movement steps. So we have those that stay due to cold temperatures and those that move because they're not constrained by the temperature. So next we calculate those that are actually moving into a segment. So say this is segment I, now we're moving into a segment, say H, and those crayfish move into that segment. Then we calculate the number of individuals that move from I to H, which is a multinomial random variable with calculated from those individuals available to move and this movement probability pi, which we assume in this estimation framework that it's Dirichlet distributed, which is a common conjugate prior to the multinomial distribution. And then this movement part links back into that first model that I talked about, the abundance and the removal model, because the abundance at the next time step at each segment is informed by the population that just moved into that segment. So that's how they're all related. And those are all the steps. So we just did them all. We calculated crayfish that removed, then population change, and then some of them moved or stay. But you might be asking me, Brielle, what about that generating model that you described earlier? So I won't be diving into all the equations for that model, but it's quite similar to the estimation model, but I have H structure. So I'm going to describe kind of briefly what the H structure is doing. So first, with the removal model, so we have the population divided into 4 H classes, 0, 1, 2, and 3 and older. And only 1, 2, and 3 and older are able to be trapped and removed because they're large enough to fit into the traps, and so those are the ones that are able to be removed. Next, we have the population change model, and we model a few different dynamics. So we model monthly survival, which is denoted by the orange arrows, and then we model yearly age transitions. So the crayfish get older, which is denoted by the black arrows. Then we have yearly fecundity, so how the new crayfish become with the fecundity. And so this population change model is a matrix population model. But again, I won't be diving into the equations, but I'd be happy to talk about that if anyone is interested. Then with movement, we assume that the young age 0 individuals always stay in their current segment, and ages 1 through 3 and older, they're able to stay and move. So in the generating model, something also important to note is that we have more informed parameters. And one of these parameters that we've been working really hard on and quite in depth is movement. And as many of you know, modeling movement in river systems is really difficult because it's not linear, it's not radial, and it's biased towards one direction. So it's not symmetrical, and it's pretty hard to model. So when creating our movement probability matrix, we scaled it by the distance and whether movement is upstream or downstream. So we have this little crayfish in here, and crayfish says, I like to stay home, but if I move short distances downstream. So the movement probability is highest staying home, and then it likes to move downstream rather than upstream. So it likes to go with the flow. But also we incorporate river forking, which was a fun and challenge to implement. And I'm happy to explain this process to anyone who's interested. But just briefly explaining it, it involves creating a movement probability matrix that allowed crayfish to move either upstream or downstream and a combination thereof in order to move to a different fork. And so it accounted for the distances and upstream, downstream movement in the whole framework. So I'm going to describe the setup a little bit. So again, just as a refresher, we have these two models, the generating model, estimation model, and they kind of feed into one another. So in our model, we just modeled 10 river segments. So I have been working really hard to try to capture the whole spatial extent, and unfortunately, I won't be able to show those results today, but I'll show just 10 river segments, which we assume are the most downstream river segments towards the Columbia River. And so we modeled this for 6 years. So we go through that whole cycle for 10 thirds, year 4, 5, and 6 up there. And the initial population abundance was informed by a stable age distribution. And then the removal alternatives involved crayfish being removed at 4 segments each June through September. Each of those segments had 10 traps, and they were laid out for 10 secondary periods or trap nights per primary period, which you can think of as months. So this is the general setup that I plug into my computer. So as a reminder, we're doing adaptive management. And so a big concept of adaptive management is that we use management to learn. And Kylie quoted this. He's a proponent for adaptive management and said, policies are experiments, so learn from them. So I ran a few different experiments, which they all tested different management alternatives. So first we have a no control scenario where I don't have any crayfish being removed. Second, we have a growth, what I call growth scenario, which is where we remove where population growth is the largest. And so where we remove each of those June through September was informed by that estimation model. Then we have another kind of scenario where which I call abundance, which I will remove crayfish where population abundance is the largest. So each of these scenarios were run for just 2 simulations, but in the future I'm going to have lots of simulations within here. But for model intensity and computation stuff, I'm just showing you 2 simulations in my results. And so each of these simulations varied in their generating parameters. So they were informed by 5 different dispersal kernels where upstream and downstream movement weights were different. And the age class removal and survival probabilities were different. And also the age class becoming rates. So these were the 3 different experiments that I tested. And in my results, I will call them decision rules. So hopefully that's clear with these. I'll say decision rules, and there'll be no control, abundance, and growth. So let's move on to results. So as a warning, these results are very, very, very preliminary. So they do not represent the full extent of the John Day River system. And in general, they should be taken with a grain of salt, but I'm showing them to you to show you how I'm going to interpret these results in the future. So keep that in mind. So going back to the beginning of the talk, we represented, or I described these means objectives, which involved controlling by minimizing population abundance of crayfish, containing by minimizing their spatial extent, and preventing, which was minimizing their movement downstream towards the Columbia River. So the current decision rules that I have only help us with this first objective right now. And but I'm going to kind of explore how they performed in the other objectives just in these preliminary results today. But first, I'm going to talk about this first objective, which was the minimizing the population abundance. So in order to see how well we did in controlling by minimizing population abundance, we need to investigate the actual population abundance and what it looks like under these different scenarios. So we often care about what the system is actually doing. So I will show results from the generating model, which simulated that true system dynamics, and with the management being informed by the estimation model. So I will show you the mean total population abundance. And what I mean by that is that it's the population abundance summed across all of the segments and summed across all of the age classes for each month. And I'll show this for each of the 3 decision rules. Abundance, where we remove where population abundance is the largest. Growth, where we remove where population growth is the largest. And no control, where we don't do anything. All right, so what do we have here? So we have, this shows that at the beginning, the population abundance is kind of similar with all the different decision rules. But through time, the no control scenario has a larger abundance. And then at the final time, the no control scenario has a larger abundance than all of them. And the growth scenario has the lowest. So looking at that, our objective to minimize population abundance of rusty crayfish, we would want to choose that growth scenario because the population abundance is the lowest. So let's look at those other 2 objectives of containing by minimizing the spatial spread and preventing by minimizing downstream movement. So to understand how we performed in these 2 objectives, we need to look at the spatial distribution. So I'm going to represent the spatial distribution just for the growth scenario in this plot. And the other scenarios follow a similar trend, but I'm just going to show that scenario right now. And so what I'm going to show you is an animation that shows population abundance summed across all of those age classes for each of the 10 segments through time. All right, so let's restart. All right, so what we see at the beginning is that through time, the population kind of was the same through all the segments, but then the crayfish spread downstream and population becomes more abundant as they spread and move downstream. And so, because it's easier to move downstream than upstream. So once we're in that last segment, it's more likely that they'll stay in that final segment than moving back upstream because it's really hard. So that's the spatial distribution through time. And I'll just let it run again so we can look at the pulsing. And the pulsing was the when bursts were happening. But we want to look at the population distribution at that final time, so after that 6 years of management. So this is a plot that I'm going to show you of population abundance across all the segments at the final time period under each of the decision rules. And so we can see that for all the scenarios, the population becomes more abundant as we move downstream. So that's a general trend for all of them. But let's look deeper into the two scenarios that we care about because they had lower population abundance. And so as I mentioned earlier, one of our objectives is to contain by minimizing the spatial extent of rusty crayfish. But none of these scenarios are preferred in this because all of the crayfish, well, every segment has crayfish. And so no scenarios win in this objective. But let's look at the objective of preventing by minimizing downstream movement towards the Columbia River. So in order to understand that, we have to look at that final segment, the most downstream one. And we can see that the population abundance at that downstream segment is the lowest for that growth scenario. And so that's the one we would choose to maximize that objective. So let's look at these objectives one more and kind of count scores, I guess. So first, with the control by minimizing population abundance of crayfish, the growth scenario is preferred. And then containing by minimizing the spatial extent. No scenarios are actually preferred in that one. And then preventing their growth downstream towards the Columbia River, the growth scenario is preferred. So if we kind of keep that in mind, maybe you would want to choose the growth scenario. But again, as a reminder, this was very preliminary, so I'm not saying anything about how management should be done. But this is just how I'm analyzing these preliminary results. But we had these two different models, and so what I just showed you was the generating model, which represented that true system dynamics. But let's compare that with the estimation model. So the estimation model will be solid lines, and that generating model will be the dotted lines. So we can see that the estimation model greatly underestimated true population abundance. And that's something I'm going to look more into as I continue working with this model. So that's something I'm kind of trying to figure out. But a general question that I hope to answer is potentially whether we could better inform the estimation model with additional data streams. So maybe including detection, not detection, telemetry data, or other types could help us get better estimates of the truth. So I will be continuing to work on this model for a lot of my next chapters and projects, and some of my next steps include increasing the spatial extent and the spatial units that I have. I'm going to model additional alternatives and add more scenarios for those alternatives, because what I just showed you were two scenarios or two simulations for each of the alternatives. Then I'm going to introduce additional data streams, which is a major component of my third chapter. So right now I just have removal data that helps us understand invasive species dynamics and management efficacy. What if we had detection, not detection, telemetry data, or other data streams? So I'm wondering if we integrate these different data streams, would we better understand the system? Would we maybe manage better? And so that's something that I'm going to continue to work on. And also, I will apply this framework for flowering rush management in the Columbia River. That's another aquatic invasive species. It's an aquatic invasive plant that's very kind of emerging downstream towards the Columbia River. And so my goal in those later chapters is to understand that more and apply the adaptive management framework with more data streams. And just as a little tidbit, they're really aggressive invader that produces these dense mats, as you can see from this photo. And so that not only causes ecological consequences, but also recreational loss, because I don't know about you, but I do not want to swim in that. So that's what I'll be working on later on. So what are the takeaways from this project? First, I hope you know now that adaptive management is used for making recurrent decisions under uncertainty. So this figure kind of represents, in a broad sense, what adaptive management is. We have our action, We monitor, we assess, we manage, monitor, assess, and continue. Second, that the forward simulation that I've been describing with the estimation and the generating model and moving forward through time, that approach can incorporate more complexity into the system and inform rules of thumb management strategies in comparison to what has typically been done with stochastic model approach. And third, this framework can be applied to many scenarios and integrate additional data streams to inform decision making. And that's what I'm going to work on in the future. And so this approach, this forward simulation approach, is pretty novel, and it's come with its challenges, but I'm excited to see how I can test this with different, with the flowering rush and adding more different data streams. So today, I hope you learned that adaptive management is a crucial tool to help us make smarter decisions. So thanks for listening to my talk, and I would be happy to answer anyone's questions.
That was awesome, Brielle. Let's give folks online a second to type their questions, and then we will take questions from us now. Or
how are crayfish aged?
They are aged by their size, and I think some different surface length, I believe, is how they're aged.
I just asked because in like marine systems with crustaceans, it's harder to age structure model them. So, well, you probably know Lee did the size transition matrices using. I was just kind of curious how you got away with doing age.
Yeah.
But that kind of answers it.
Yeah.
for a related question to that, can you talk about why the age 0 individuals are not trapped in the room?
Yeah, so those ones are often too small to fit into the traps that are typically used to capture the crayfish. And so, which is actually something maybe I'll incorporate later on, which is a cool question to see whether or not our management alternatives are trapping. What if we could remove those smaller guys? What if we did like kick staining and actually remove them, or some other method to remove those small crayfish? How would that affect the population and management? But yeah, those older crayfish are more likely to join those traps, and actually the removal probability is higher as the crayfish are older, because the kind of mean old crayfish like to be territorial, and so they're more likely to be stay in the trap, because I guess the trap had food and they just want to, which is kind of funny. So they'll stay in that trap. So yeah, the removal probability increases as crayfish age, but the youngest crayfish won't be removed. Yeah, because they're too small.
Cool. Okay, I have a question from online. Teresa Tom says, "Hi Brielle, thank you so much for your presentation. Could you speak a little about trapping bias for crayfish and how you're addressing this in your modeling? And with respect to prevention, how did rescue crayfish get in? Thanks."
So trapping bias, could you clarify that?
Teresa, I can unmute you if you want, or you can type your question again. But I think you kind of got at it. I'm guessing she's getting at age bias, right? Maybe.
Yeah, it might be that or sex bias.
Yeah, the model isn't sex-based, but that's something I can think more about. Yeah, the bias is towards the ages in the model, and I guess the generating model. What was the other part of the question?
How did they get into the generator?
Oh, yeah, so they were introduced by a school teacher, most likely. They have these crayfish in their classrooms to learn about how crayfish, maybe their ages or through time. They just had a crayfish as their pet and science experiment, I guess. And I guess they had multiple of these and they introduced them into the river system because probably killing their class pet was something emotionally maybe damaging if they did that. So that's why it was introduced into that system. But in other areas, often they're spread by being a bait, like they use crayfish for bait. But in the John Day River system, it's most likely by a school teacher. So tell your school teacher friends to not release their critters into the water.
Oh, okay. I was just gonna ask if it's currently assumed in the model that the whole John Day River is pretty like equal suitability, like equal ability to sustain similar sized crayfish populations, I guess, or not incorporating any like habitat heterogeneity.
Yeah, the only habitat heterogeneity is the temperature. And so some areas in the whole river system is too cold for crayfish to even establish. So some of those segments assume that, yeah, they can't go into, or they won't survive in those segments because it's too cold. Yeah, so that's the only thing that I have now. Sarah?
Yeah, thanks, Brielle. That was awesome. I'm fully objective about that. So that underestimation is crazy, huh? So I wonder, I don't think it should be, but is it possible that it could have to do with the travelable area issue?
Maybe.
Yeah, I wonder if we could play around with that and see if that's what's going on there. Just make the travelable area 1, basically.
Yeah.
Trying to figure out what else could be causing that.
Mhm.
So if it is a travelable area, it might be that we're just estimating a different population.
Yeah.
So I think we have a multiplier in there, right? So. Exactly, but that might be something for us to explore.
Good questions. Brian?
I have 2 questions real quick. So you said that like there's like some territoriality and especially like these like cranky old man, like age-based, is that incorporated into your movement decisions at all? Like if you have a population and maybe an older population in a segment, are other individuals more likely to move in your modeling?
So in my model, I don't have age structured movement.
Okay.
I just assume that the youngest crayfish stay in their current segment, but the other ones are available to move. But that's something interesting.
Okay. And the other thing that I thought of was, I don't know if you've considered like a model where you have this like these 2 intervention types, right, with abundance and growth rate. And have you done anything where like the wildlife manager could choose year to year which intervention to apply as opposed to just having to stick with one or the other throughout the simulation period?
Yeah, that's actually something we've talked about,
Okay.
seeing whether or not.
That seems like the advantage of this adaptive management approach would be being able to adapt your approach as you.
Yeah, for sure. And I think my model has the flexibility to do that right now.
This is a really great talk, super interesting, thank you. I have a few questions. So first, and this may just be that I'm unfamiliar with ecological models like this, but how or do you conduct calibration or validation with a model like that? Do you have any empirical data that you're using for that? The second question is related to the movement model and the hydrology of the system. And so you had this model where they can't move upstream and they kind of move downstream. And so I'm just curious how the hydrology system does or does not play into the potential of crayfish, particularly downstream. And then the final question I had was about the estimation model. So it looked like at the end what you were showing is that decisions are made based on expected values for various outcomes. And so I was curious whether in the long run you're considering incorporating like probabilistic or unprobabilistic approaches to avoid low probability but really high risk outcome.
Yeah, that's a great question. Sorry, the first one was again.
Yeah, sorry. Some calibration.
Calibration, okay. So in the generating model that represents the true dynamics. Most of the parameters were informed by literature, or informed by a previous model that Julian and another grad student once did that was actually an individual-based model. And so I used some of those parameters to inform what's going on in the system. And then I have, with each of those different parameters, I incorporate uncertainty because they're drawn from different distributions. And so say I have maybe a survival rate for each of the age classes that were informed by the old model, but in the one that was already published. And so and then this model, I give some variation on that because who knows if that's actually right or not. So we want to give some uncertainty on that.
I guess just a question. I mean, could you compare just the no intervention scenario?
Yeah, that's true. That's a good point. Yeah, I can do. I haven't really done a whole lot of model validation, especially with the estimation model, because it's just been taking a long time to get it to work. And that's what my next steps are, is assessing convergence in those models and stuff.
Yeah, I'm familiar with this type of ecological model. So I was also wondering about hydrology in the system. Is that, I don't know, maybe in this kind of model that's.
Yeah, this isn't, the hydrology isn't incorporated into this model. In the individual-based model, it did incorporate kind of slope of the river, kind of like how it was, which is something I could include in this model, but it's already kind of complex already that I just kind of had to cut some things off.
Well, I mean, in some ways, right, Brielle, you're letting crayfish, there's a higher probability portion of the population moving downstream. Than
Yeah.
upstream, right? So
Yeah.
hydrology is baked
Yeah.
into that because they're more likely to move downstream because of hydrological stress, shear stress.
Yeah.
I guess, and this might just reveal how little I know about crayfish, but I was wondering if, like, I mean, if you had a really flashy month, for example, a constant fall, maybe there would be more migration downstream.
Yeah, that's definitely true. But I didn't incorporate those events in it, which it probably could be incorporated if I just shift those movement probabilities maybe 3 times.
And then, yeah, sorry.
No, you're fine.
I was curious about the estimation model. How it considers forward.
Oh, sorry.
Whether the decisions being made are probabilistic or whether it's based on.
They're right now based on the mean values in the estimation framework, but that's a good point that they could incorporate some sort of uncertainty around that as well.
Yeah, again, this is really cool.
Thanks.
So one more thing just to add on the first question, Brielle, is you can think about this sort of going back to the setup phase, right? So we talk about this idea of double loop learning and adaptive management. One of the ways you validate a model in adaptive management is you use it, right? And you sort of say, well, we're using this to make predictions and we kind of predict this and we seem to be learning and it's not doing very well. And so periodically people will kick out into that setup phase and say, we really need to re-examine our model itself. So anyway, that's another way to think about that idea of model validation is you're validating it by using it and it's either working for you or it's not.
I have one more question for you.
Yeah.
And then we wrap up.
Cool.
So on the preliminary results that you showed, it seemed like you had the growth intervention was doing better on every metric. And so what would you do, I guess, if you had like a mixed scorecard on those needs objectives?
Mixed, sorry.
Like if the, yeah, there. Sorry. Yeah, like let's say that the abundance scenario was doing better on growth. One more slide back. That one. Yep.
Okay.
Yeah, so like in both on the control and prevention means objectives, this growth scenario was preferred. And so why would you act if on the abundance scenario was prefer it on like prevention, but growth scenarios prefer control. You see what I'm getting at?
So it's like they weren't
Like if they
aligned.
indicated, yeah, different.
Yeah, so that would be really interesting to want to go back to your stakeholders and be like, okay, what's the objective that's most important to you? And then maybe you would weight that. So what I didn't weight any of these objectives, but that's something that's often done in these problems. So it's like the manager said, okay, I really, really care about preventing downstream towards the Columbia River. That is really, really important. So maybe that scenario would be preferred, even if other ones. So it all depends on. Yeah, cool, that's great.
Awesome. Should we give Brielle a round of applause? So folks online and in person, I guess, join us next week. We've got Ben Augustine presenting from Brielle, and he's going to talk about abundance estimation when you can't identify individuals or at all. So